All right, in this example, we're looking for the volume bounded above by z equals the square root of 16 minus x squared minus y squared, and below by the xy plane and x squared plus y squared less than or equal to 4. So we're looking at essentially underneath this surface here, which if we look at the formula for, we can recognize, well, if I did square it, I would get z squared, and I could put all those squares on one side. This is really an upper half sphere. So if we picture it, we've really got this upper half sphere where the radius of it is the square root of 16, so 4. So it's a sphere of radius 4, and it's just the positive square root, so we only have the upper half. Really, in a way, it would be okay if we couldn't fully see what that was, because what we have then is I can still represent my region R, where essentially what we're doing is we're cutting that on the bottom by that xy plane, and then we're essentially cutting it with the equation x squared plus y squared less than or equal to 4. So if we think about what x squared plus y squared equals 4 would be, well, it would be a cylinder of radius 2, because what we would see is we would essentially have a circular region where when I look at x squared plus y squared equals 4, we recognize that as a circle of radius 2. So we're going to kind of have this portion on the inside here cut out, and then essentially we're drawing a cylinder up from there. So it's kind of like my full solid that we're looking for the volume of is essentially like a cylinder with a little domed piece on top of it, if you can picture that. So my actual region R, which is one of the most important parts that we need, really is coming from here, that x squared plus y squared less than or equal to 4. So we've got that circle of radius 2 centered at the origin, and we want less than or equal to it, so we're really inside of that circle is our region that we're looking for. So we need to find a way of representing that region. And then what we're going to be looking for the volume is we would be doing that the double integral over the area of R of that function of z, so of the square root of 16 minus x squared minus y squared, doing that area, or that integral with respect to area, which could either be a dx dy or a dy dx. Now there's a couple different things about this problem that we might recognize that polar coordinates could be a good choice. One thing, well, our region is circular, which is nice to do in polar coordinates, but probably more importantly in this example is that this function that we're integrating is not necessarily a particularly nice function, right? Having squares under a square root oftentimes causes some issues. So, but we can see that we've got that minus x squared minus y squared, which would convert pretty nicely to polar coordinates. So let's try and convert over to polar coordinates. So here we can find our bounds in terms of r and theta. Again, they're both very nice, where r is just going to come out from 0 to 2, and then we do need the full circular region of that. So theta is going to go 0 to 2 pi. So we can go 0 to 2 pi, the integral from 0 to 2. And then when we think about converting things, remember that, well, I could convert in what x and y is, or I can remember that x squared plus y squared is r squared. So really the fact that they're both subtracted, this is going to be 16 minus r squared. And then don't ever forget that we need our r dr d theta. Now in this one, it would have helped us out a little bit actually to remember that we need that r dr d theta. because if we take a look at trying to do that integral of just 16 minus r squared under a square root, it would be pretty challenging to do. If we take a look at it now, though, the fact that it's r dr d theta, we are doing our dr integral first. Thinking about how to do this then, we would probably recognize the composition of the underneath the square root with that derivative on the outside. So we would do a u substitution where u is going to be 16 minus r squared, and then du would just be negative 2r dr. So I would have a negative 1/2 du is r dr. And then why don't we just go ahead and convert our bounds. So we've got that when r is, let's do our lower bound first, when r is 0, well, u is going to be 16 minus 0. So we've got u is 16. And then when r is 2, we've got that u is going to be 16 minus 2 squared, which is 4. So u is going to be 8. Oops, sorry. 16 minus 4 is 12. We can do math. 12! So putting all that back in then, we're going to see the integral from 0 to 2 pi times the integral from 16 to 12. Remember to keep those bounds in their correct places. Of the square root of u. And then that's times negative 1/2 du, and then that's still all d theta. So what we end up with then, we can convert u to the square root of u is a power of u, so we'll have the integral from 0 to 2 pi, the integral from 16 to 12, we'll have negative 1/2 u to the 1/2 du d theta. So taking a look at this integral with respect to u, have the integral from 0 to 2 pi. Power rule says bring that power up by 1, so it's going to go up to 3/2. So we'll take that negative 1/2 and divide it by 3/2, which is multiplying it by 2/3. U to the 3/2. That's going to get evaluated from 16 to 12. And this is still d theta. So we're going to have the integral 0 to 2 pi. We really have a negative 1/3. Because those 2's canceled out. We'll have 12 to the 3/2 minus 16 to the 3/2. Which we can clean up just a little bit, so we would have a negative 12 to the 3/2 doesn't really simplify much because the square root of 12 is irrational. And then taking a look at these then, 16 though, the square root of 16 is 4. So then we really have 4 cubed, which is 64. So we would have plus 64 over 3 d theta. If we take a look at it though, all of that together is still just a constant. So when we take this integral d theta, we're going to have negative 12 to the 3/2 over 3 plus 64 over 3 all theta. You could have had each of them times theta, but it's the same. And then that's going to be evaluated where theta goes from 0 to 2 pi. So we plug in 2 pi, we'll have that negative 12 to the 3/2 over 3 plus 64 over 3 all times 2 pi. And plugging in 0 doesn't give anything new. So we could clean this up more if we want to. If you do really play around with the square root here, the 12 to the 3 halves, and like split up what that integrates to, right? We have like the square root of 12 cubed. You can split that up if you want to. You can altogether, with distributing the 2, get negative 48 square root 3 plus 64 times 2 is 128. So that would be all over 3, and then all times pi as a simplified answer. So if we remember for this one of the reasons we recognized a desire to switch to polar coordinates partially came from r, but also partially came from the function itself, seeing that it would simplify the integral to switch it to polar coordinates.